Okay, everybody, let's continue with the discussion of yesterday. Uh, so far, we have tested what we call the I2c byte write algorithm for a single write, and we have tested random read algorithm for a single read. Then we had tested the byte write for consecutive writes as well as the random read for consecutive reads. This is the status of what testing we had done related to the I2c protocol. So next what we need to do, the testing is the next two algorithms, which I will be showing you in a short while. That is called as the page write algorithm and the sequential read algorithm. So we have to look at the page write algorithm and implement the page write algorithm. Then the sequential read algorithm, we have to look at it, implement the sequential read algorithm, then test that. So that is again coming under reading the theory, then developing the protocol or implementing the protocol, then testing that part. So once we do that, we would have completed our test to a maximum extent with respect to this one device 24C01. After that is completed, what we can try to do is we can add a few more 24C01s on the same bus. So on the same I2C bus, I can add a few more 24C01 devices and make some changes in the hardware connectivity and try to access those few more devices. So maybe I'll take up around additionally another 2 or 3 devices. So that may make it up to completely 3 devices or 4 devices on the same I2C bus. And we'll be able to access each of these 4 devices of the same type on the same I2C bus. How we can do that also, we'll see it. So that will be the next level of protocol testing. So first, let us try to complete the page write and the page, the sequential read. Okay, so just I'm first going to minimize this and open the PPT part. Right. Yes, people. Can you see the algorithm waveforms? Please confirm. Are you able to view the algorithm waveforms? Okay, so look at this algorithm waveform. The algorithm is titled as page write algorithm. So it begins with a start condition. So master issues a start condition. After master issues a start condition, then master issues a slave address with write operation. So I'll annotate here for you as I'm doing it. Okay, master issues a start condition. After start condition, then master issues slave address with write operation. Then master takes an acknowledgement from slave. Then master issues the start address of sequence, the start address of the buffer whose sequence we want to write into. Okay, because it's a page write, so a page write supports up to it may slightly vary from one manufacturer make of 24C01 to another manufacturer make of 24C01. Suppose if it's an Atmel manufacturer of 24C01, it will support up to 8 bytes. Sometimes some other make may say may support up till 16 bytes. So that is not really a very critical issue. So it depends on the manufacturer how he has designed the page write algorithm. So here the page write algorithm, we have to first give the start address of the 8-byte sequence which we want to write into, 8-byte address sequence which we want to write into, or we have to give the start address of the 16-byte address sequence which we want to write into. So that is basically given here as the word address. Okay, after that, then we go take an acknowledgement from the slave. Then we issue the first data to be written to that sequence of addresses. Then take an acknowledgement, issue the next data for the sequence of addresses. Then issue the take acknowledgement, issue the next data for the sequence of address, and this can continue up till, let us say, 8 for some device, some make of device, or say 16 for some other make of device. So 8 or 16, this is what I know. Maybe there are some other maximum limits for other devices. I have not studied all the devices, but for the two devices which I had studied, it supports up till 8 or 16. The simulation one supports up to 16, but we will restrict ourselves only to 8 because the hardware kit of the hardware kit which is used in Vector Institute is having a version of the controller. It's having a version of the EEPROM or make of the EEPROM which uses up till 8 bytes. So we'll restrict ourselves to 8 only. Hence, this data that you're going to write can be minimum 1 byte, and it can go up to a maximum of 8 bytes. You can write 1 byte, 2 bytes and stop, or else you can write 1 byte, 2 byte, 3 bytes and stop, or you can write up till 8 bytes and stop. So each byte that we are writing will automatically get stored in the appropriate location. First address has been given, so first data will get stored in first address location. Second data will automatically get stored in the next address location, because internally the EEPROM device will internally increment the address pointer automatically. So user does not need to specify the address the second time. He has to specify the start address the first time, and the rest of the addresses will be automatically incremented by the address pointer. So it's an automatic operation in the page write. So this can go all the way up till 8 bytes. And after 8 bytes have been written, we take an acknowledgement and finally issue a stop condition. After issuing the stop condition, then again we need to give a delay of about 10 milliseconds for internal write cycle. So these 8 bytes that have been written may probably go into some temporary buffer. So if they are going into temporary buffer, they have to be copied from temporary buffer to the actual memory locations. So this requires an internal write cycle of 10 milliseconds. Just as we used an internal write cycle for the previous write algorithm, here also we need to use an internal write cycle of 10 milliseconds delay. So this is about the page write algorithm. So how many events are involved? So I'm numbering them right now, the events involved. Okay, just a moment. So this is one event. This is the second event. This is the third event. This is the fourth event. This is the fifth event. This is the sixth event. This is the seventh event. So sixth and event will, as per the number of bytes that you're going to write. So if you're going to write 8 bytes, so 6 and 7 event are 2 events. 2 events multiplied by 8. That is going to be what we call 16 events there. 6 events will take place or can take place in an iterative manner. Okay, these 2 events, 6 and 7, can be taking place in an iterative manner, which gives rise to 16 events totally. And after the 16 events, maximum, we have what we call the stop event. Iterative manner, then you can issue what we call the 8th event. So in this way, you can count events in this manner. Is this understood, please? say something if you have any confusion regarding this algorithm. Anybody has any confusions regarding this algorithm? Can please come out and express. I hope the algorithm is understood. This is a different algorithm as compared to the two algorithms that we have dealt with so far. Those algorithms only deal with one memory access, one memory location access, write into or read from. This deals with set of memory accesses, writing. Okay, people, no doubts here in this algorithm. Can I move ahead then? Yeah, data goes up till n plus 8 or n plus 16, depends on the actual hardware device that you're using. So if the make of the hardware device is Atmel, it will go up till n plus 8. If the make of the device is some other make other than Atmel, it may go more than 8 or some other maximum number. Is it okay, people? Understood about this algorithm? Okay, so what I'm going to do is now, if you have understood this algorithm, this is the theoretical discussion about this algorithm. Now we have to go for implementing this algorithm. That is called as development, program development or protocol development. I need to develop this protocol after the theory has been understood. So to develop this protocol now, again, I'm going to minimize this. Okay, let me just remove this. Right, and I close this and bring it up here. Are you able to see the coding screen? Are you able to see the coding screen? Okay, now coming to the I2c.h file. Okay, coming to the I2c.h file, I am going to add what we call the prototypes for this operation, that is U8, not U8, we'll go for void, let us say I2c device page write. I2c device page write. So I'll give there U8 to indicate slave address, then U8 star, which is the buffer address, and then U8, which is the number of bytes which we want to write. Okay, buffer start address and the number of bytes we want to write. And what else? We have slave address data, number of bytes which we want to write into. Okay, anything else? Let us see. Buffer slave address, start address of buffer, and number of bytes I want to write into the buffer. Okay, let's check this out. And here also void. Okay, right now we'll look at this. So I2c device page, right? Now coming to the I2c.c file. Here I'm giving the comment page write algorithm. So void I2c device page write. So here U8 is slave address. Next is U8 buffer start address, buffer sequence start address. U8 buffer sequence start address. And what else I'll put here? U8 number of bytes to be written. Okay, number of bytes to be written. One more I'm missing. Buffer sequence start address. Pointer or let's say star p of 8 bytes. Okay, star p means pointer to 8 bytes. So let's close this. Let me add that also in the prototypes. One more pointer star U8 star. Better I put this here and I put this here. And let's cut this and paste it here. Okay, guys, people, you're able to see the code now. So this is what I'm trying to think. Now going for the implementation. So opening the curly brace and going for I2c start. Next I2c write, that is slave address with write option. Next I2c acknowledge. Next I2c write I2c write. So put here buffer sequence start address. Buffer sequence start address. Next I2c acknowledge. Okay, guys, let's take n bytes. So n bytes is the variable. So coming here, while n bytes greater than 0, while n bytes greater than 0, n bytes minus minus greater than 0. So it's a post decrement. So I'll go for I2c right. I2c right star pointer to 8 bytes and put there plus plus, which is post increment. Then go for I2c acknowledge. After the n bytes completed, then we have to go for stop condition. So I2c stop. After that, we give the delay of 10 milliseconds for the internal write cycle. Okay, people, are you able to see the code implementation for the algorithm? Please confirm. People, are you able to see the code implementation for the algorithm? Please confirm. What is the question? C5, what is your question about while? What is your question? The while loop, what is the question there in the while loop? The while loop is trying to write either 1 byte or 2 bytes or 3 bytes up to n number of bytes, maximum 8 bytes. So I'll be passing a number there. In the function, I'll be passing a number up till how many bytes which I want to write. Okay. Because according to the algorithm, first master issues a start condition, then it gives slave address with write operation. Master takes an acknowledgement from the slave. Then master writes buffer start address, buffer sequence start address. Master takes an acknowledgement from slave. Then master issues first byte, takes an acknowledgement, then issues second byte, takes an acknowledgement, issues third byte up to maximum 8 bytes. So the n bytes which I want to write should be a number which is what we call not more than 8. It should be 8 or less than 8, but cannot be more than 8. So I can try to add some condition there also in the while loop if I want. While n bytes is uh, greater than 0, but maybe we can try to add some logical condition that it should be while n bytes greater than 0 and n bytes not greater than and n bytes not greater than 8. N bytes should be greater than 0 and n bytes not greater than 8. That is n bytes less than 8. Less than or equal to 8. Like that also we can do it. So just by changing the loop conditions, we can do that. So right now, let it be like this. So my n bytes value will be this. Now, if I come to the I2c write, this is a pointer to 8 bytes. Then after that, take an acknowledgement. Once we come out of the loop, we issue a stop condition and then give a delay for write cycle. So I'm giving the comment here. Issue start condition. Next, slave address plus write operation. Next, Master takes acknowledgement from slave. Next, issue start address of buffer sequence. Next, master takes acknowledgement from slave. Next, loop write loop for data write loop. Data write loop for n bytes. N should be less than or equal to 8. N should be less than or equal to 8. Or you can also say 1 less than or equal to n less than. So I've just given a mathematical expression there. N ranges from between 1 to 8. That's the thing. Then issue data. Master takes acknowledgement from slave. Issue stop condition to end session. Okay. For internal write cycle operation of or device. So I have given what we call the comments there. Okay, next let me close the function. So I have closed the I2c device page write function in this way. Now coming to testing the code. Code has been developed, protocol has been implemented. Now testing the code. So to test the code, let me come to this file and save this file as eprom3.c. Okay, and let me remove this and add that one. So we remove this right now. In place of this, let me put here, let us say 9. I'll go for I2c device page write. Okay, I2c device page write, and give here the Control C and buffer start address 00. And let me directly give here my name, SHEKHAR78. Welcome 7. Okay. So institute. Okay, I just wanted to give something. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm just giving this. And here I'll give 8. Take a variable for iteration and remove this for I equal to 0, I less than 8, I plus plus. Okay, people, have you seen the code now? Please confirm. Have you seen the code for testing? Please confirm. So I am calling I2c device page read, which will try to write 8 bytes, which is the character value of 1, 2, 3, 4, 5, 6, 7, 8. Then using the device read, which we had already developed, I'm trying to read back those 8 bytes, store them in the array of 9 size, and ending the last one with null character. Then I'll string compare what I have read with the return value 1, 2, 3, 4, 5, 6. So if I'm able to read back what I have written correctly, then the status LED should complement. Otherwise, until then, the status LED will be in on state. Default status of the LED will be on. After comparison is successful, it should go to off state. So let us test this now. So save and cross compile. I'm compiling the code now. I'm cross compiling the code. We happen to have some warning, uncalled segment I2c device write. So because we're not calling the write function, we are getting that warning. So not a problem at all. That is one warning. The second warning is argument conversion pointer to non-pointer. Pointer to non-pointer. Okay, maybe I've, this is a buffer sequence start address. So I need to give buffer sequence start address. Okay, sorry, small mistake over here. It should be buffer sequence start address, and make a correction here in the prototype. Right, we have that one warning which can be ignored. Now opening the Proteus file, simulation file. Opening the Proteus simulation file. Is the Proteus simulation file visible? Okay. Hex file path is already there. Okay, hex file path is already there because of yesterday's thing. Now I'm going to run the code. So I'm going to run the code. So let us see. Okay, I have ran the code. First part of the code seems to be working fine. We can see that there. To some extent, okay, there is a small mistake there also. So 1, 2 was eaten up. In the memory it is showing. 1, 2 was eaten up. 3, 4, 5, 6, 7, 8 was available. So maybe some small bug is there in our code. Let me try to check it out. What could be the bug? 8 bytes I'm writing. Slave address with write operation. I2c device read slave address with write operation. Okay, that restart condition I had commented yesterday for demonstration. So slave and save and cross compile. Once again. Yes, people, did you see the output? See, once again, I'm showing it. You can see that in the I2c memory window, we have the values 1, 2, 3, 4, 5, 6, 7, 8. Okay, people? We have the values 1, 2, 3, 4, 7, 8, 5, 6, 7, 8, and those values have been read also. That read operations can be seen over here, starting from 31 till 38, and comparisons have been done to be true. That's why the LED switched off. Initially, status of LED is on. You can see the LED is on. Read operation is done, and after 5 seconds, it switches off. People, did you see the output? Okay, so that means our implementation seems to be fine because the testing was successful. Now let's try to implement the other algorithm for sequential read and also test that. So going back to the slide, where was the slide? Just a moment. So going back to the slide, now you can see the slide here. So we have successfully implemented the page write. Now we have to implement the sequential read. So look at the sequential read. It goes as follows. First, master issues a start condition. Okay. After master issues a start condition, then master issues write operation. Then master issues, master takes acknowledgement from slave. Then master issues the buffer sequence start address where reading should begin from. Buffer sequence start address where reading should begin from. Then master takes an acknowledgement from the slave. Okay. After that, master issues a restart condition. Then master issues slave address with read operations. After that, master takes acknowledgement from slave. Then master reads first byte. So I'll just call it as RB1 read first byte. Then master gives acknowledgement to slave. Here master was taking acknowledgement from slave. In these cases, master was taking acknowledgement from slave. Here now master is giving acknowledgement to slave. Let me use a different color here. So master is giving acknowledgement to slave. Then master reads the next byte to master gives acknowledgement to the slave. Master reads the next byte. Let us say 3. Master gives acknowledgement to slave. Master reads the next byte 4 and gives acknowledgement to slave. Means depends on how many bytes we want to read. So we can read n number of bytes. Restriction has not been given here up till how many number of bytes has been can be read. For write, it is restricted to 8 bytes. If you try to write beyond 8 bytes, then the previous, suppose if you're trying to write 9 bytes, okay, if you're trying to write 9 bytes, first 8 bytes will be written, and then the 9th byte will overwrite in the position of the first byte of the 8 bytes. Of course, for the simulation, because I'm using the simulation of not Atmel, it supports up till 16 bytes, I think. Theoretically, I'm telling you that when you try to write beyond 8 bytes, then the subsequent bytes will overwrite the previous initial bytes in the page write sequence. But in the case of the sequential read algorithm, there is no restriction on how many bytes can be read. So up till n bytes, it can be read. Restriction is not there. It can be beyond n, beyond what we call 8 also. But let's not confuse ourselves very much. Let's restrict ourselves to maximum 8 for our purpose only. So first byte read, give an acknowledgement. Second byte read, master gives an acknowledgement. Third byte read, master gives an acknowledgement. For the last byte, which has to be read by the master, after master reads the last byte, it issues no or not of acknowledgement onto the bus as an indication to the slave that no more further reads will be performed beyond this point. No more further reads will be performed beyond this point. And then finally it issues stop condition. Please confirm, did you get the algorithm? If not, you can raise your queries. Please confirm if you have not got the algorithm with some queries. If not, I'll go ahead in the implementation and testing. Word address is, see, the device that we're talking about, 24301, is having only a byte address which ranges from 00 to 7F, because 24301 is having only 128 bytes of memory. So 00 to 7F. Suppose if you go for 24302, it will have 256 bytes of memory, which goes from 00 to FF. But if you go for 24304, it will have 512 bytes of memory. So that 512 bytes of memory means the address will go beyond 8 bits. If the address is going beyond 8 bits, then we have to send 2 bytes of information for address, because 1 byte of information for buffer address will not be sufficient. 512 bytes will have a 2 byte address. That's called as a word address. Is it understood? HE6 J12 J2. Any more questions, people, regarding sequential read? Okay, then, if no questions, I'll go for the implementation, and then let's try to complete testing today. So let me clear this and close this. Okay, and again come back to share. So now coming to the I2c.h, I'll just copy this and paste it here and call it as sequential read. Sequential read. So I'll just use the same order of arguments. Next, coming to the definition. You are able to see the coding screen. Are you able to see the coding screen? Okay. So I'll just copy this part and paste it over here. And let me just name this as sequential, sorry, sequential read algorithm. So as we saw, the sequential read begins with a start, then it again goes ahead with a slave address with write operation, then takes an acknowledgement from the slave, then buffer sequence start address. So buffer sequence start address buffer sequence start address, buffer sequence start address read, buffer read buffer sequence. I'm just thinking of a name. Okay, buffer sequence start address I'll give only, let it be there. Then acknowledgement. Next, coming to the number of bytes to be read. This remains as it is. So here, n minus minus greater than 1. I2c read okay. So I2c read and what is read has to be stored. So P8 of 8 bytes, P8 8 bytes of I need to give equal to read. Start plus 8 bytes. If I give that plus plus also, it's fine. Let us see. Okay, guys. Hope you're following. So the implementation I have written in that way. So whatever n bytes I'll give, if I want to read 8 bytes, I'll read first 7 bytes in the loop, and the last byte will be read outside the loop, and the master has to give no acknowledge. After reading the last byte, then we assign the null character there. Then master issues stop condition. Delay, I think, is not required in the read operations. So save. I have implemented the communication algorithm. Now we need to test it. So for testing, let me go for the file again and save it as 4.c and add that. Semicolon after null. Where did I miss? Semicolon after null. Okay. I missed a semicolon. Thank you. So source group add files. Okay, I've added the 4th main file, and I'll remove this statement and put there I2c device sequential read. So let me just copy this part, copy and paste it here. Slave address buffer sequence, and then I have to give the here, let me give S. Let me check out with this again. Buffer sequence pointer to the 8 bytes. Okay. Okay. So we cross compile and define pointer to 8 bytes. I2c device page write function already has a body. Is it page write? Okay, this is sequential read. Sorry, sequential read. Save and cross compile. Right, we have warnings that reference made to unresolved external symbol I2c master. So I need to go to the defines and click on this. Save and cross compile. Next, we have 2 warnings: uncalled segment I2c device write and uncalled segment I2c device read. So let's try to fix those things also. So I'll go for hash define I2c device write enable, put there as 0, and hash define I2c device read enable as 0. And coming over here, let me put here hash if I2c device write greater than 0. I2c device write enable greater than 0. And if similarly hash if I2c device read enable greater than 0. I'm going for conditional compilation. Hash and if. Okay, people. I hope you are seeing. Now save and cross compile. Okay, we have uncalled segment I2c restart. So restart is not being called. So we can avoid that also and give here hash define I2c restart enable as 0. Coming here, I2c restart will be somewhere. Hash if I2c restart enable greater than 0 hash end. Okay, people. So all those routines, whether I want them to be there in the part of the compilation or not, I'm able to decide using the conditional compilation. Now save and cross compile. We have it there. This is your code reduced. Now let us check. Whether it is there. I'm making a slight modification over here. Let me copy this and paste it over here as a global variable and add some location. Let us say at some location 30h 0x30 absolute location, and let the I variable here be local, that being global. So save and cross compile. I unreference local variable, so we can remove that also here because it's not being used. Save and cross compile. There we are. Okay, people. Now switching over to the Proteus. Is the Proteus visible to you? Is the Proteus visible to you? Since the hex file path is already given, now executing the code. So something seems to be wrong in our implementation. So write is working fine, but sequential read is giving us some garbage. As you can observe here, so we have to try to fix this tomorrow because time is up. Start slave address with write operation is fine. Acknowledgement is fine. Start address is fine. Restart condition not available. Am I using restart condition down there? Not available. Oh. Do we have a restart condition in the this thing? Let me check. I forgot there the implementation of restart. Let me go back to the communication algorithm. So we have after slave address with after buffer address, slave address with write operation and buffer start address. Then we have a restart condition. Okay, yes, I missed out a restart condition. So I need to add the restart. That's where I missed. So go back to the implementation and go for the restart condition. Where are we? Buffer start, device page write. So I need to give a restart condition here. So I2c restart condition need to give there as per the algorithm. I forgot that. And then device address with read option also I need to give. So go back to the code. Then I2c write slave address odd with 0x01 device address with read option. Then I2c acknowledgement. Yes, I think now we get it correctly. Save and cross compile. Then again come to defines and restart activated. There we are. Are you able to see the Proteus simulation file? Proteus simulation. Okay, now I'm running the code with the correction of the bug. There we are. And successful. Please claps from your side. So successfully we have implemented the protocol and tested the protocol. The LED also gave us a nod. The LED also gave us a nod, indication that our read and write is successful. What I have written and what I have read is fine. So if I just look up in the memory, this is the I2c memory, and I can also view in the internal memory of the 8051 30H location. Just hold on. Internal memory. There you can see in the 30H memory location, we have the values 1, 2, 3, 4, 5, 6, 7. Other values, whatever they are, don't bother about that. That's some internal operation the compiler is doing in the C implementation. So what is to be observed is those set of memory locations starting from 30H onwards, we have been able to read the 8 bytes. Okay, people, have you seen the output? So with this, we close with today's demonstration. Okay. This is the main file. Yeah, I will upload it. Don't worry. I will upload it because I'm doing modifications time and again. As you can see that yesterday, what was the file and what is the file today? It has been modified or upgraded like that. So once I complete the entire demonstration related to this device, then I will upload it. Okay, V19H7P2. Let me complete it totally and close it. Once I close it, then I will upload it. Otherwise, again, you will be confused with the modifications and updates that I'm making. That's what I mean by protocol development. See, protocol development is not just about mugging up the code. It's like developing the program and testing and making modifications, developing, testing, making modifications like that to suit our requirement. Okay, people, we stop here for today. Thank you for your patience. It's past 1. I think today we had a short break compared to the previous breaks also. So please be prepared tomorrow for the set of questions. Tomorrow I'll be giving 20 questions, 15 to 20 questions in two polls. One poll can only support 10 questions. So I'll try to prepare 15 to 20 questions. Minimum 10 is for sure. Maximum it may go to 15 or 20. So a few questions on TCP/IP, few questions on ARM, few questions on what we call I2c protocol. Okay, people, please be preparing. Okay then, bye-bye.